Okay, we are excited to have our last speaker of the session, Eric Mazumdar. He is an assistant professor at Caltech in computing and mathematical sciences and as well as economics. He did his Ph.D. at UC Berkeley with Michael Jordan and Shankar Sastry. His interest broadly is in machine learning with strategic agents for societal problems. And today he's going to tell us about machine learning and strategic agents.
Yeah, so today I'm going to talk about machine learning in the presence of strategic agents. And I'm going to focus on kind of a dynamic view of the problem and try and point out some insights for algorithm design in these kind of more complex scenarios. And if you have any questions, feel free to jump in or anything like that. I'm happy to make this more of a discussion. So this doesn't work. We'll do that. So I'm going to start with a very, very obvious observation that we're increasingly interacting with learning algorithms, unknowingly or knowingly every single day. So when we're ordering something on Uber Eats, reading the caption on the New Yorker cartoon, or even ordering something on Amazon, there's some form of a data-driven algorithm running in the background of all of those processes. And I think this just goes to show how these algorithms have just been deployed across everyday life. But we know that there's no shortage of basically examples showing that these algorithms really struggle in the face of strategic behavior on the part of their data sources. So this is one of my favorite examples. It's this phenomenon known as Surge Club that happens on Uber or Lyft. And Surge Club goes like this. A group of Uber drivers will go to a certain part of the city. So they'll go, this is LA, so they'll go to Beverly Hills. All of the drivers will turn off their app at the exact same time. The Uber surge pricing algorithm notices it's just lost a huge supply of drivers in Beverly Hills. So it starts surging the price there. And then those drivers, turn on their apps, collect the higher price, and go on with their day and do this presumably somewhere else. The problem with that is that the users are being faced with artificially high prices because these drivers are effectively gaming the surge pricing algorithm. And as an algorithm designer, this is not at all what I wanted my algorithm to do. But I think it just goes to show the types of complex strategic behaviors that algorithms have to deal with when they're actually deployed into the real world. If they do it too much, yeah. But I think sometimes the demand on the user side is actually pretty inelastic. So they'll just take because they have to get to work or something like that. So they're more just price takers for a lot of the case. But you're right. If they exaggerate too much, then of course they'll just push people out of the system. And this happens kind of all over the place. I was on vacation in Europe, and then one person told me not to use Ubers because drivers are messing with the algorithms all the time, which I thought was really funny because it was just someone on the street telling me that. So the other kind of negative example of what happens when machine learning is used in situations which people have something to gain out of the outcome is that the data itself can be strategically manipulated. So this is a study that was done, I think, in the early 2000s, which looked at giving subsidies based off of this poverty index score that they had calculated in Colombia. And so you could see in 1994 when they calculated this score for the population, it looks kind of Gaussian. The threshold for getting this subsidy, was this red line. And, they went along. They kept on going with that. 1997, they ran the program again. It was the exact same thing. In 1998, the explicit algorithm for how they calculated this poverty index score, along with the threshold, was actually released to the public. And then you see that people start to game misreport their data. So basically, everyone slightly to the right of the threshold misreports their data just to get the subsidy. And then by 2003, this is a totally useless metric. And I think this just goes to show you how these algorithms or the decision rules that we actually deploy into the real world will inevitably be gamed and are just going to be subject to strategic manipulations no matter what. And so I could go on and on with these type of negative examples, but I think the takeaway is that deployed learning algorithms just will inevitably be faced with strategic agents, and we actually have to design our algorithms from the ground up to deal with these type of scenarios. And I could go on and on. The OECD is worried about algorithms and price collusion. Self-driving cars have to deal with this all the time, and so on. So to get to the bottom of why this happens, I want to think about our traditional approach to machine learning. And that's this kind of toy problem where we have a static environment where we're getting IID data. We're training a decision-making algorithm on this data. And then it's going to make decisions based off of this data. But basically, the environment is modeled as not moving or adversarial or just IID. But I'd say the real situation in which we're deploying these algorithms looks a lot more like this picture, where we have decision-making algorithms operating in uncertain dynamic environments that are maybe evolving over time. And these algorithms are competing, not just with other algorithms, but also with people, all of whom might have their own, objectives in mind. And so the goal of my work is to try and make sense of this picture here, and maybe in a little piecemeal fashion. And so today I'll talk to you about two works that tackle problems in this general area. The first is generally about how we should learn from strategically manipulated data. And in particular, what are the important kind of facets of algorithms when our data is actually being gamed. And the second is about a problem in learning and matching markets. So I'm going to start with this, this problem of learning from strategically manipulated data. The general problem I want you to keep in mind here is that if agents adapt to deployed models over time, what types of solutions can a decision maker hope to achieve? And this is joint work with Tiana Zernick at Berkeley and Mike Jordan also at Berkeley. So this problem generally lives in this area of strategic classification. And let me just see if this actually works. Oh, yep. Nice. It generally lives in this area of strategic classification, in which there's a decision maker who wants to minimize their prediction loss. And they deploy a predictive model into an environment, and then that environment has a set of strategic agents who want to get favorable predictions out of the decision maker. So you and to do that, they report strategically manipulated data. And so you have this kind of feedback loop between the predictive model and the strategic data on which it's deployed. So importantly, the strategic agents and decision maker in this problem both adapt to each other's actions, where the actions are the prediction or the data. So this is a form of distribution shift, but it's a very particular form of distribution shift that we're interested in, which is distribution shift due to strategic manipulations. And the general question in strategic classification is, what's the natural equilibrium solution for this type of game theoretic interaction, and how is it achieved? So just to introduce a little bit of notation, we're going to give the decision maker the parameter theta. Those parameters might be neural network weights, linear regression parameters, the classification boundary or something. On the other side, we'll have a group of strategic agents, and they're going to report data that's just going to be summarized by this mu. And mu is going to be the decision of the entire population of strategic agents, which is a modeling choice. So in this case, it might be the mean of some normal distribution. So the decision maker is going to have a loss that they want to minimize that depends both on mu and theta. So when they deploy theta and the agents take action mu, they suffer some loss. The strategic agents are going to have some loss, some risk that they would like to minimize also, given theta and mu. And that's basically the setup that we're going to consider. There we go. So this problem has garnered a lot of attention in the past few years, starting kind of with Moritz Hart and some of his collaborators in 2016 until much more recently. But by and large, basically all of the work in this space has modeled this interaction as some kind of a stackover game. So a stackover game is a game where one player, the leader, basically moves first, and the other player moves second and must respond to basically the leader who's committed. Importantly, in all of these past works, they've always modeled the decision maker as being the leader in this interaction. And so the general interaction that has been looked at in the past has been like this. You have a decision maker that announces a model theta, strategic agents that observe theta and then choose mu. And basically, if you think about it in the more game theoretic way, what happens is that given a theta, the mu players are just going to learn how to best respond. And then theta would like to optimize basically this objective here, which depends on this best response map, and find what's known as a stackover equilibrium where they lead. So this is a toy setup, but it's a pretty decent model for some particular processes. I think the most common one in this literature is that of a decision maker announcing a credit scoring system, and then people are taking actions to improve their credit scores. So how do you design a credit scoring system given that just the existence of that system is going to incentivize people to take certain actions? And that's kind of the general approach that's been taken in in strategic classification in the past. The real problem in all of this literature is that this best response function is not really known. And so the question, throughout all of this is how should the decision maker optimize, given that they don't know how, this exact utility are, and they don't exactly know how people are best responding. So again, the general approach in strategic classification has been to learn through repeated interaction with an environment. So you have a decision maker who repeatedly interacts with agents to find a stack over equilibrium. So at time t-1, they'll put a model, the population will best respond, t, they'll best respond again, and then so on and so forth. But the goal is to design basically learning algorithms such that the loss goes to the Stackelberg loss as t goes to infinity, using some kind of online gradient descent or something pretty simple. So this model has some limitations, quite a few limitations. The first is that the burden of learning is solely on the decision maker. So agents are assumed to instantaneously best respond. And the second is this is, as I mentioned, a good model for really slow processes like giving out loans or college admissions. But it's not necessarily a very good model for online platforms or e-commerce where decisions are happening at a much faster pace. So in this work, we generalized a standard strategic classification model to allow both players to gradually learn on their own timescales. So in particular, the decision maker might update their model every t rounds. On this t timescale, the population might respond to whatever model is out there. In particular, they're not best responding. They're just maybe learning how to respond over time. And they might be on their own timescale too, which might be unknown to the other side of this problem. And throughout this work, we just assume that the population of agents is no regret, meaning that whatever sequence of losses that are put in front of them, they'll basically learn to optimize, in the infinite limit. So just to make it very simple, we'll focus on two relevant modes of relative timescales. The first is where the decision maker is very, very slow relative to the agents. In that case, the agents are taking so many steps in each essentially epoch that they can basically converge to a best response, in which case we'll basically recover the first setting that I just talked about of college admissions or credit scores, where they basically see the deployed model is fixed and they can learn how to best respond. But maybe more importantly is this opposite scenario, where the decision maker is really fast relative to agents. In this case, for every 2 shifts of the population, the decision maker who's training a model can basically learn how to best respond themselves. And these are basically, this is a better model for online platforms like YouTube or Instagram or Uber, because these decision makers are extremely reactive to small changes in the population. And something that's pretty interesting is if you're YouTube or Uber or something like this, you can actually choose which of these scenarios to be in. You could learn very slowly or learn really quickly. So you could really choose which of these scenarios to be in. And what's interesting is just by tuning how fast you're learning, so by tuning your update frequency, the decision maker can combine that with really simple algorithms and learn to drive no-regret strategic agents to a stackable equilibrium with either order of play. So in particular, at equilibrium, it's actually possible for the agents to lead and the decision maker to follow with their best response, simply by tuning your update frequency. So the second result that we're actually able to show is that in several standard learning settings, it's actually preferable for both players to be in that stackable equilibrium, which is the one in which the order of play is flipped compared to the one classically looked at in strategic classification. So I'll give you a little bit of intuition for how we show this. The first case, as I mentioned, is the case that we've looked at in kind of classic strategic classification work. In which case we define an epoch as the time between model updates of the decision maker, and under sufficient regularity assumptions on the 2 losses, and assuming the agents are no regret learners, if the decision maker uses a black box online convex optimization algorithm, we could show that they will converge to a stackable equilibrium where the decision maker plays first or leads. So maybe that's not surprising because that would recover just the classic stackable, the strategic classification work. But the difference now is that the population is no regret, and they're not just immediately best responding. So importantly, the underlying assumptions here is that the decision maker has no knowledge of the loss of the population or this best response map. So they have to interaction through these black box. They have to interact through these black box optimization algorithms. And the second kind of really important assumption is this sufficient timescale separation. So agents have to make at least enough updates per epoch to basically get this type of property. And we can make all of these results, into finite time convergence rates by assuming the agents are using particular no-regret learning algorithms like online mirror descent or something like that. And we can even give lower bounds on the length of the epochs needed for these results to go through. And the proof techniques and ideas are all coming from dynamical systems theory, like 2-timescale stochastic approximations. But maybe the more interesting case is, as I mentioned, this case where the decision maker is going much, much quicker. And then under the same no-regret assumption on the agents, the decision maker just has to do online gradient descent on their own loss. So not even black box optimization. And you get the kind of converse result, that if the decision maker is going much, much faster than the population, then they could basically converge to a stackable equilibrium where the agents lead. Yeah, so when I say online black box, I mean the update of an online black box optimization algorithm. So in that case, it might be like a gradient step using a certain gradient estimator coming from that optimization algorithm. Yeah, exactly. It's like all of these type of step sizes and things like this. So as I mentioned, this is a new equilibrium for the strategic classification literature because it's the one where the order of play is flipped. So in essentially what we're showing is that there's another reachable equilibrium concept in these strategic classification problems, which can be reached just by essentially tweaking how fast you're learning. Yep. Yeah, that's a good question. So the loss function in this case just has to be strictly convex or strongly convex, and this will go through. The important thing that we really need is for that best response function to be sufficiently smooth. Yeah, you can think of it as maybe the mean of the distribution that's being chosen, or some kind of statistic that summarizes that distribution. So we're essentially modeling the entire distribution as one player that can move in concert. That's a pretty strong assumption, actually, and we're working on how to relax that to assume that the population is made up of a lot of infinitesimal individuals, and this type of behavior might happen as a mean field type behavior. But in this work, it's just one player. So if they have a higher order? That's a very, very good question. Yeah, this whole work is under the assumption that the agents and both sides of this are actually pretty myopic. There's no kind of long-term planning in any of this. Part of it is basically because this population is made up of a lot of individuals, making this assumption that the population is full of myopic individuals kind of makes sense because individuals would have no effect on the general movement of the population in a long-term sense. From the point of view of the decision maker, it's a little bit of a strong assumption to assume that they're not myopic. They could probably do much better if they tried to plan through. But in this case, yeah, this is still just the first work in this area. Yeah, you could think of them as just one agent as well. Yeah, we're assuming that we have this, essentially this one agent can model the entire movement of the population. So this no-regret behavior is coming out of the large-scale no-regret behavior of the whole population. That's, I agree, the strong assumption, but it's kind of necessary in that individuals have no effect on the movement of a population. So a population can only really affect a learning algorithm through some kind of aggregate motion.
And that's assumed to be a no regret.
Yeah, exactly. The aggregate is assumed to be no regret. Yep.
They're not completely unrelated?
Yeah, so in this case, they're completely unrelated. You could, maybe if you're in a more adversarial context, R could just be the negative of L or something like this. But so that you have a zero-sum game. But in this case, yeah, we've made no assumption on how they're related.
So you're given two arbitrary convex functions on which you're doing gradient descent at different rates.
Yeah. And so what's interesting so actually the important thing here is that the decision maker is using a black box optimization algorithm, and you have this timescale separation. Because if you have that property, it will guarantee you that you're essentially differentiating through the best response function because of this black box oracle. Yeah, it's a little bit surprising that you could do this just essentially by using these black box optimization algorithms and this, timescale separation. Yeah, it'll converge, in expectation with decaying step sizes and things like this. Yeah. So, the second result that I mentioned is that we have a result on the preferred order of play in these type of games. So, in general, any order of play can be preferred by any player. But leading is always no worse than the best Nash equilibrium of these games. But if we make some assumptions on the structure of the player's losses, we can actually say something about, what equilibria both players prefer. So, in zero-sum games, just by the basic max-min inequality, you have this property here, which is basically saying that following is never worse than leading. But more interestingly, in these kind of more machine learning contexts, we can actually say something general too. So imagine that you have a logistic regression problem where you have a set of data points, these red data points and these green data points. The reds are the ones who are going to be negatively classified. They might be the ones who don't get loans, will default on their loans. The greens are the ones who won't default on their loans. The loss of the leaders is going to be some kind of logistic regression problem over this data set. And we're just going to assume that the entire population of agents here just wants to maximize basically get as close to the decision boundary as possible. But they're optimizing subject to this kind of budget constraint and how much they can move. And what's interesting is just in this context here, both players actually prefer the stackable equilibrium where the agents are leading, which is, again, the one that's flipped compared to the rest of the strategic classification literature. And so both players get lower loss at this stackable equilibrium where the learner is leading, or the decision maker is leading. The decision maker is following. And there's cases where both inequalities are strict, and we can actually show that this is true for other kind of linear learning problems like linear regression or something. So,
can you switch back and forth between leadership?
You can, but then you'd have to change the frequency at which you're learning and re-optimize and things like that. But under these no regret assumptions, you probably could. So just to show you that this actually works, we have the faster player is just going to run simple gradient descent. The slower player is just going to run gradient descent without a gradient. So this is your online convex optimization algorithm. And you could just see, depending on whoever is faster, they converge to a stackable equilibrium with different payoffs. And these are under different conditions in that logistic regression example. Great. So the takeaway from that first line of work is just that if agents are no regret, a decision maker can lead the game to a stackable equilibrium with either order of play. So if the decision maker updates very, very slowly, they'll lead at equilibrium. And if the decision maker updates very quickly, they will follow at equilibrium. But the real takeaway here is that classic machine learning assumptions can stop being true in strategic settings. So faster learning algorithms or faster converging algorithms might not always lead to better outcomes when you're using them in strategic settings. You have to think about your learning rate and all these type of parameters. And faster may not always be better, basically. Zero regret in that they're always playing their best response or something like this. Yeah, I mean, if they're always playing their best response, then they're essentially just doing this. And if the other player does a gradient descent without a gradient, you'll converge to the other one. Great. So in the second part of the talk, I'm going to focus on a slightly different problem, just switch context a little bit. And the main question here is going to be really about how should firms learn preferences while competing over sparse resources. And it's going to get back to that problem that you mentioned, actually, which is about how do you explore and exploit, but we'll add this third dimension, which is how do you compete. So learning through interaction has been looked at a huge amount in the machine learning literature, but normally it's always been in this context where a single agent has to learn about their preferences through repeated interaction with an environment. So in this case, we have our toy algorithm here has multiple options at each round, and it has to choose an option to learn about its preferences over those options. the general problem here is really how do you deal with exploration, exploitation, and in the really simple stochastic bandit setting, we know all the optimal algorithms for it. We have algorithms that match lower bounds and so on and so forth. A missing piece to this, at least to me, has always been about how do you learn about your preferences if you have to also do it while competing for over limited resources with other strategic agents in the environment. So in this case, we might have 3 algorithms competing over these 4 options at each round, and that adds a certain amount of non-stationarity to these bandit environments. So we need to design algorithms that explore options, exploit their knowledge, and compete effectively with the other strategic agents in the environment. But we also want to go a little bit further than adversarial bandit algorithms that just deal with other agents as being purely worst case. And we want to say something a little bit stronger than just saying we're going to converge to coarse correlated equilibria, which is generally the guarantee that we get by using no regret algorithms. Yep.
Good question. So if the rates of learning of the
Mm-hmm.
range, then do we get to some
Yeah, so in the previous stuff, it's a little bit different of a setting. In that case, my guess is that we would get to some kind of coarse correlated equilibrium. The problem is it's not entirely clear what those look like, right? If you're talking about coarse correlated equilibria over like a continuum of actions and things like that, it's very unclear what those look like. Cool. So today I'll be kind of focusing in on a case where there's a huge amount of structure, and that's the setting of matching markets. So we have agents that are in matching markets. They don't know their preferences, and they have to match with firms to receive noisy samples of the utility of their match. And we're going to assume, just for simplicity, that firms have known preferences over the agents and that they're essentially myopic. And so the interaction will go as follows. At each round, an agent will request to be matched to a single firm. So in this case, we have 2 agents request to be matched with firm 1. The third agent asks for firm 3. And then basically, if multiple agents ask for the same firm, only the firm's most preferred agent will get the match, and everyone else will get no feedback. And then agents, if they're successfully matched, they get a sample of their utility of the match. And if they don't get the successful match, they just get a collision or no feedback at all. And that's going to be the really simple kind of interaction protocol. The general idea is, or the general question in this problem is really how should agents learn in these markets, and how do we benchmark our algorithms? So, Vijay already kind of went over this. The full information solution is really well known. It's just going to be this deferred acceptance algorithm from Gale Shapley. Gale Shapley I don't need to go over, but essentially every agent is just going to be requested to be matched to their most preferred firm at each round. And then if they collide, they just move on to the ones on which they've never collided before until everyone kind of converges to a stable match. So this benchmark, this Gale Shapley algorithm has a lot of nice properties when viewed from the lens of convex optimization, online learning, which is really that it's a decentralized algorithm in that agents make their own decisions based solely on their own kind of local information. They don't have to know anything about the other agents in the market. It's communication and coordination free, and the agents are not coordinating their actions or communicating their actions across rounds. It's partial information. Agents don't need to see who they collide with or know the firm's preferences at all. And despite not knowing this or anything like this, it will still converge to a stable match. And basically, that's a very, very nice property that is very hard to get out of online learning algorithms. So our approach for the next, or this part of the talk, will be how to design algorithms with all of these properties, except that agents don't know their preferences, so they have to learn about their preferences. And we're going to hope that agents can have low regret with respect to a stable match in these problems. So this exact problem has kind of gained a lot of attention in recent years, going back to Das and Kamenika in 2005, and more recently by Lydia Liu and some of her collaborators. Most of the past work, or essentially all the past work on this kind of bandit approach to matching markets, has really, assumed away one of the problems that I had, one of the features that I had on the last slide of Gale Shapley. So, generally they were looking at centralized algorithms or decentralized algorithms where you could see the entire market or something like that. And we really want to do something without observation of the market, and without this centralized decision making. So we really want simple, decentralized algorithms that can basically learn without coordination or observations of the market. So our approach to this problem, and Chin Mei, I should say, is who's the main author, is right there, and he'll be presenting a poster on this later today, or maybe tomorrow. Yep. Oh no, so they are synchronized into time steps. So the one thing that they're doing is just at every round they have to. Yeah, they know how they have how time goes exactly, but they can't, coordinate their actions at every time step or something like that. They all have to take independent decisions. They don't know who's in the market or anything like that.
And if you don't allow that, that synchronization, then what?
Yeah, then all bets are off basically. Yeah, it would be just pure chaos, I'd say. Yeah. So our idea to this approach is really just to combine ideas from stochastic and adversarial bandits. Again, we don't want to rely fully on adversarial bandits because then we wouldn't get very tight guarantees. We just get this coarse correlated equilibrium. But we need some adversarial band algorithm there to deal with competition. In this case, where we don't really observe much about the environment. But we're going to use a stochastic bandit algorithm like UCB or Thompson sampling to deal with the statistical problem of learning your preferences and exploiting. And generally, we'll use this adversarial bandit algorithm to deal with the competitive part of this problem. So the algorithm is really simple. You'll basically have a stochastic bandit algorithm. You'll have indices, so it might be your upper confidence bounds, it might be your Thompson sampling samples. You'll just choose a firm based off of those indices. You'll feed that firm to an adversarial bandit algorithm. You'll have one for each firm in the market. And then you'll just flip a coin. And if the coin is heads, you'll actually request to be matched with that firm. If the coin is tails, you'll just take that firm out of your set and just repeat the entire process. And you'll keep on going. And then if the list of firms is empty, you could just choose any firm. So then if you're successfully matched, you can basically update your stochastic bandit algorithm with the feedback, with the reward that you get. And then no matter what, you're going to update the adversarial bandit algorithm. So you're going to update it with a loss of 0 if you successfully match, with a loss of 1 if you collide, and then 1/2 if you decide not to choose that arm. Yep. Yeah, so you're using a stochastic bandit because there's uncertainty over your preferences. And so you want to basically understand the expected utility of that match. Yeah, because of the non-stationary environment that's coming because everyone else is also learning. Yep. So the nice thing about this algorithm is that it's fully decentralized and that individuals only have to make their own decisions. They don't coordinate with anyone else. Obviously, no one's communicating or coordinating, and agents only need to observe whether or not they collided on a match. They don't have to observe with who they collided or anything like that. So we can only really give guarantees in these problems if we make assumptions on the markets. So in particular, what we need to do is basically assume that there's a unique stable matching, and we need something a little bit stronger than that. Namely, we need this assumption of alpha reducibility, for which we need this definition of a fixed pair. So we'll assume, so a fixed pair is just a pair of agents and firms that prefer each other to every other pair in the market, or every other agent or firm in the market. And basically, a market is going to be alpha reducible if every submarket in this market, this matching market, has at least one fixed pair. And the nice thing is that this guarantees us the uniqueness of a stable match. And an example of this is like the serial dictatorship setting. And then we need to assume something about the adversarial bandit algorithm to really get the tightest guarantees. So in particular, we'll assume that they're doing mirror descent with a log barrier regularizer. And this was an idea that Haipeng Luo and his collaborators came up with in 2017, which was used to get these really tight adversarial bandit regret bounds. Yep.
So can you give us some intuition on how restrictive or general this assumption is?
Yeah, that's a good question. It depends on, it obviously restricts the types of markets you can look at, but there are some important classes that are in here. So namely the serial dictatorship, where if everyone has the same preferences over. So if any side has the same preferences over the other side, then that will fit into this. If there's, every person has a different preferred firm, then it kind of fits into this as well. So there are some important classes that fit in. It's definitely, not every possible market fits into this. So this adversarial bandit algorithm that we choose is this one that gives you path length regret bounds. And this was, as I mentioned, an idea proposed by Haipeng Lo and his collaborators. Bubeck and others have expanded on this. The general idea is you're going to update your probability, the coin flip probability according to this update rule. So it's just basically online mirror descent with just a different regularizer. And you're just going to, given your loss, update your probability. But the nice thing then is if every agent uses UCB or Thompson sampling in that stochastic bandit block, so you could choose your favorite approach to bandits, and you use this adversarial bandit algorithm, then for each agent A, we can guarantee that their regret with respect to the unique stable match is going to be logarithmic over the gap squared. And this gap squared is a little bit unavoidable because of the collisions. And it showed up in all of the other past works that had to rely on stronger assumptions. So the interesting thing here is that this logarithmic regret is still possible with bandit feedback and in this kind of competitive scenario. To give you an idea of how we get to this result and a little bit of some of the scaling factors involved, the nice thing about this path length regret algorithm and our alpha reducibility assumption basically lets us say that the number of collisions is upper bounded by basically a logarithmic factor, and the number of possible matches you can make on a certain firm, and then you kind of recurse backwards using this alpha reducibility structure. So something that's a little bit hidden in this big O notation is that the dependence on the number of agents and the number of firms in the markets depends on the actual alpha reducible structure. So this can range from basically linear in A and F to something that's exponential in A and F, though we're pretty sure this is just a proof of this is an artifact of our proof technique, because as I'll show you on the next slide, this exponential case really happens in the serial dictatorship setting, and you basically only the worst agent pays this exponential bound. And as we see, this isn't really something that we see when we run the algorithm. So just to give you some numerical experiments, yep. Oh, the analysis is not tight, yeah. And just to give you some intuition for that, we're just going to randomly generate matching markets and use our algorithm. So we have 5 agents, 7 firms. The firms have fixed preferences over the agents. I think it's just 1, 2, 3, 4, 5. And they all have the same fixed preferences, and the agents are just going to randomize their preferences. And they're either going to use Thompson sampling or UCB randomly. And you just see that they really quickly learn to play the stable match, which is the one hidden in blue and behind the green arrows. And on the right, we just see kind of the regret of our algorithm over time. And no matter what, they will converge to, or we see that they converge to this optimal match. Great. So just to wrap up, I presented kind of 2 works that take real baby steps on trying to understand this larger picture of how do we learn in the presence of self-interested strategic agents in these dynamic environments. And I think we've only really scratched the surface, but I think it's a really kind of exciting research area. So with that, I just want to say thank you, and I'm happy to take any questions. Yep.
Yeah, I guess building on the earlier question, at least in the numerical experiments, how often did you generate an alpha reducible market?
Oh, here? I mean, because we fixed the firm's preferences, we always had it.
Okay,
Yeah.
never mind.
Like, yeah, the firms always had the same. Yeah.
In that case, I have one question. So, so you mentioned this fixed pair condition. So how tight is that? Like, is it necessary if you don't have that condition for every submarket? Then, like, you're going to lose on your significantly lose on your result?
Yeah,
Final
so
guarantees?
basically the reason why we need this fixed pair and this alpha reducible condition is to really understand how the other agents in the market affect your learning. Because in general, it's very hard to characterize, the probabilities which they may be choosing arms and things like this. And so that allows us to basically recursively, show that, the first fixed pair gets, logarithmic regret. The second one then must get logarithmic regret, and so on. In general, we see that these algorithms are pretty agnostic to that structure. So if you run it on markets on randomly generated markets that don't satisfy this condition, we pretty much always see that they have this logarithmic regret. But just understanding how to prove in those scenarios where the environment is totally non-stationary because of the other agents is pretty hard.
So you expect it to go through. It's just that we don't have a proof for it.
Yeah, because in a way, the serial dictatorship setting intuitively should be the hardest, because in a way, the last agent, the least preferred agent, has to wait for everyone else in the market to converge before they can actually start to converge. And in a way, that should be the hardest context for anyone to learn, because you basically have to wait for everyone else in the market to learn.
Not then let's thank the speaker and all the speakers of the session.
Cool. Thanks.